Hi everyone, this is Hans from Tundra Feed and Supply Company. Today we're going to be taking a brief look into the concept of efficiency in programming, both in scientific and practical terms. We'll look at big O and big omega notations, with brief mentions of big theta and little o as well. We'll cover a few examples to see how big O and big omega function, then we'll briefly mention a few popular sorting algorithms and their efficiencies. In industry, you may have little overlap with actively choosing algorithm implementations. However, it is always critical to develop with efficiency in mind. So why does efficiency matter? Well, let's look at a game example first. Say in our game, we have projectiles and we need to detect if they hit an enemy or an obstacle. Programmatically, what this means is we need to check if every projectile hitbox has collided with any of our enemy or obstacles. In other words, we iterate over our entire array of projectiles, which has a variable size as the player can fire as many as they want, and for every projectile, iterate over our entire array of enemies or obstacles, which is also an increasing number as we spawn more enemies each level. This check has to happen every frame. If you're making an RTS, or even if you're trying to do pathfinding in the real world, for instance with an autonomous rover, whenever you give an order to units, all of the selected units independently need to run A-star pathfinding to find how to get to their destination. These complexities add up and can drastically slow down your application or increase the memory usage as well. We measure the space and time complexity of algorithms through something called big O notation. The applicability of big O notation and the challenges of efficiency stem far beyond game development and exist in all domains of programming. So let's look at what big O notation is. So initially, we have what this notation is named after, which is big O itself. Now, big O is generally the worst case scenario for the algorithm. What is the worst possible space and time complexity that the algorithm could take? From there, we then have big omega, which is the opposite. What is the best case that the algorithm may take? From there, we then have big theta, which is the lower and upper bound of an algorithm. Sometimes this is used as an average of how the algorithm performs. And then finally, we have little o. So the formal definition for little o is f of x equals little o of g of x. If for all constant c, there exists an xo such that f of x is less than c of g of x, when x is greater than x of o. In other words, as is displayed here on the screen, the limit of f of x over g of x equals 0 when x goes towards infinity. As you can see, this leaps deeper into the science side of computer science quite quickly. And while I do want to touch upon those concepts here to give a summarized yet full introduction regarding efficiency, I'm also aiming to keep this practical. While technically your efficiency of an algorithm could be anything, there are generally several categories that algorithms are lumped into. So that's O of 1. So this is a constant. This is anything that does not have a linear growth to it. And we'll look into this more in a moment. From there, we have big O of log n, O of n. And when I say O, I'm also referring to big O, that it's the same thing. So O of n, e.g. linear, then O of n log n, then O of n squared, and finally O of n factorial. And again, there are variations in between these. These are just a general category with which algorithms are frequently ranked in terms of their space-time complexity. So let's take a look at some equation examples. So for f of n equals 100n, we have our constant of 100, but that's multiplied then by n. So our big O will be big O of n, because we're taking the worst case of this equation. And n is worse than 100, so for our worst case, it's going to be space-time complexity of n, big O of n. So from here, f of n equals 100. So there's no n attached to this. This is just 100. So this is considered a constant. So this would be O of 1. Then our next equation, we have f of n equals 13n to the fourth plus 6n log n plus 13 plus 2n. Now, when we're looking at an equation like this, what we want to highlight is the worst possible outcome when we're talking about big O. And so in this instance, when we're looking at these individual values here, obviously we can tell that n log n is more than 13, 2n is more than 13, and our largest value here is n to the fourth. So in this instance, since we're highlighting the worst case for this equation, it's O of n to the fourth. Okay, so now let's look at some practical examples through coding. So here we just have a simple program that is going to print hello world 10 times. So what is our efficiency here? So we can tell that this application, no matter what we do, is going to run 10 times. So it has an O of 1. Now, if we were to also wonder what our big omega for this is, what's the best case for this algorithm, we can tell that no matter what, I starts at 0, and it is going to iterate and print hello world until it reaches 10. And so in that instance, our best case for this algorithm is also big omega of 1. Let's move to another example. So now we have the same thing where we're printing hello world starting with I equal to 0, but I is going to print as many times as n. N could be 1, n could be 1,000, n could be a number that increases as our application runs. So in this instance, our big O is O of n, and our best case scenario, again, there's nothing happening within the for loop that would cause this to return early. So our best case scenario, our big omega, is also n. Moving on to a for loop inside of a for loop, we have both I and j both starting at 0. Both are incrementing once per loop, and each loop is running for as long as the loop is less than n. So for every single value of I within n, j also has to iterate from 0 all the way to n. So in this instance, our big O is now going to be O of n squared, and our best case scenario, since we have no exit conditions, is also going to be big omega of n squared. Let's take a look at another example. So here, this is the same as our previous example, where both I and j are starting at 0 and incrementing once per loop towards the value of n. However, we do have a return condition. If the value of I in array 1 is equal to the value of j in array 2, we're going to return early. So, in that instance, what is our worst case scenario for this algorithm? Well, it's potential that neither of the arrays share values, in which case our worst case scenario is n times n. So our O is going to be O of n squared. However, our big omega is now O of 1. Now, why is this? Let's look at what this algorithm is doing. We can tell by the exit condition that this algorithm is comparing two arrays. In the worst case scenario, the comparison that this algorithm is searching for is at the end of both arrays, requiring both arrays to be fully stepped through. Hence, we get our big O of n squared. However, this also introduces a big difference for the best case scenario, e.g. big omega. What if both arrays have started fully sorted, where the first entry fulfills the condition? What if both array contains one letter and both of those letters are A? So in this instance, immediately our exit condition would be fulfilled and the algorithm would exit. Consequently, our best case scenario is big omega of 1. So finally, let's take a look at some popular sorting algorithms and algorithms that you will frequently find in programming interviews. So those are quick sort, merge sort, heap sort, and bubble sort. It can frequently be a good idea to have the programmatic implementation of these memorized, along with their efficiencies for programming interviews, as these are fairly common questions about how to implement these or the efficiencies surrounding them. Quick sort and bubble sort both have worst case scenarios big O's of n squared, whereas merge sort and heap sort both have big O of n log n. Quick sort, merge sort, and heap sort have big omegas of n log n, whereas bubble sort has a big omega of n. And then this is the only other time that I'll mention theta here, where we're looking at sort of the average performance of these algorithms, and we can see that, again, quicksort, merge sort, and heap sort have a big theta of n log n, whereas bubble sort has a big theta of n squared. Thank you all so much for watching. I hope this can be helpful in terms of an introduction towards the more scientific side of efficiency in programming. These are important concepts to have memorized, just to be able to utilize while you're architecting any sort of application, whether you're looking to create computer vision analysis in Python or developing a game. Bigonotation is something that's always good to have in a software engineer's back pocket. So thank you, and see you next time.